You're watching a Channel 98 NBISD TV production.
Aloha! Welcome to That Geometry Show, our very special spring break edition of That Geometry Show. As always, I'm your host, Kevin Corpy. Now, I know what you're saying, so don't ask. Spring break is supposed to be about a break from school, which means a break from math. But let me tell you what I think you already know deep down inside your heart. 7 days without math makes 1 week, in more ways than one. Yeah. Well, if you are a faithful viewer and you're tuning in today, I guarantee you won't be disappointed. We are going to have a ball. Literally. We're talking about spheres, their surface area, their volume. So, download those worksheets and we'll get rolling. Lesson 26, this is chapter 11.7 in your textbook. Surface area and volume of spheres. Okay, today we do look at the fascinating sphere. Of all the shapes, the sphere has the smallest surface area for a given volume. Or put it another way, it can contain the greatest amount of volume stuff inside for a fixed surface area. It is a very, very naturally efficient shape. Now, because it's efficient and nature loves efficiency, the sphere does appear in nature whenever surfaces want to be as small as possible. For instance, bubbles or water drops, okay? Everyone's seen bubbles. They're spheres for a very, very physical reason. They're very efficient. Now, here's some other interesting things about spheres that you might notice. Spheres are perfectly symmetrical. Here's a little picture of a sphere. They have no edges and no vertices, which make them very ideal for like sports balls, like basketballs. You're not going to dribble down the court and cut yourself on an edge of a sphere. It's not a polyhedron. It's not made up of polygons. And all points on the surface of the sphere are the same distance from the center of the sphere. So here's two radii coming out in two different directions, but you can draw a radii or radius in any dimension coming out off the paper towards the sphere, and it's always going to be the same length. Okay? The fascinating sphere. We need to learn some terminology about the sphere, so here we go. A great circle is not only a fantastic circle, but it's called great for another reason. It's the circle in a sphere that has the same center and radius as a sphere. If you think about taking a circle and passing it right through the center of the circle, that circle is called a great circle. It'll divide our sphere into two equivalent or two congruent parts, which are called hemispheres. Now, the shortest distance between any 2 points on the surface of a sphere is going to be measured along a great circle path. Okay, now let's talk about a globe, because a globe is something we're all familiar with. If a particular point on a sphere is designated as the North Pole, so maybe North Pole's up here, okay, then the pole that is opposite it, or the antipodal point, is called the South Pole, and that's how we orient ourselves. The equator is actually a great circle that runs through the center of the circle, and it would look like that. Okay, and the equator is basically the biggest parallel. Okay, or the biggest line of latitude, which we'll talk about here in just a second. The way we navigate around the globe, the GPS positioning gives us two coordinates. It gives us a line of latitude and a line of longitude. The lines of longitude, or the meridians as they're also called, are great circles. They're basically extending from pole to pole, and each of these great circles has the exact same circumference. Now, if you've ever sliced up an apple into wedges, the wedges are forming the great circles. They are basically pieced out from the center. So it's kind of like taking this sphere and starting with one circle that goes all the way around and then rotating it 360 degrees. They're all going to meet at the poles, okay? And they all have the same circumference, so they all have the same diameter. Well, they also pass through the poles, and the line that connects the two poles, especially on the Earth, we know this to be true, is the axis of rotation. And our Earth does rotate around an axis of rotation, but we're slightly tilted. We are tilted at about a 23.5 degree angle. So we're kind of tilted like this up in the solar system. We're kind of rotating around. All right, so we got these great circles, which are all the same length, and they have the same circumference. Each great circle has the same circumference, which is the largest on a sphere. Now we could talk about the circles on the sphere that are parallel to the equator. So this is kind of like the lines that we get when we slice up a tomato. If you've ever sliced up a tomato, you don't slice it into great circles usually. You might slice it into wedges, but the slices that go on like a hamburger, if we took this circle and we sliced it with parallel slices like this to the equator, if we look at a cross section of each of those, they're going to be getting smaller and smaller as we get to the top and bottom. Because we're slicing it parallel to the equator, these lines are called parallels, and they really are lines of latitude. And they are all a different shape. So we have a longitudinal line, which is a meridian or a great circle, and then we have a latitude line or a parallel, which have varying circumferences. So we do use that terminology on the Earth, even though the Earth is technically not a sphere because it spins around an axis and it's kind of tapered in here around the edges. So like it's wearing a belt around the equator. And it also has irregular surfaces around it, so it's technically a geoid, but it's so close to spherical that we call it a sphere. So here's a picture of two hemispheres divided by a plane that will generate cross sections that are great circles. And we could generate two hemispheres by slicing it along any great circle. So if you slice the Earth along the equator, you get the northern hemisphere and the southern hemisphere. That's what we're used to seeing. Okay, so that's a little bit about spheres. We're going to be working with two formulas today involving spheres that will help us define some really important quantities. Okay, and guess what they are? They're surface area and volume. We're going to look at them together. The surface area of a sphere with a radius r is given by, surface area is 4 times pi times r squared. 4 pi r squared, surface area. The volume of a sphere, the amount of stuff that it can contain inside, is given by V. Volume is 4/3 times pi again times r cubed. So notice the difference. Area is a squared quantity and volume is a cubed quantity. And that's what we've been putting on our units the last couple of weeks when we've been dealing with area versus volume. Now they both have pi in it. Remember that pi is just an irrational number. There's a button on your TI calculator specifically for pi, but it's approximately 3.14. Remember, Archimedes was the first guy to give us an upper and lower bound for that. So that's a constant even though it looks like a symbol or a variable. Now, notice the variable in this equation. We really only have two in each. We have a surface area variable and a radius variable, or in the volumes case, we have the volume variable and the radius variable. So what does that mean? That means if we know r, strictly the radius of our sphere, we can find either the surface area or the volume. And on the other hand, if we happen to know the surface area or the volume, we can solve and find the radius. Okay? And we're going to do some of those types of examples today. So we're going to have several types of problems that are going to appear either in class or on our standardized tests, and we need to know how to work each one in every case. The first variety that we're going to look at today is the easiest variety. It's when you're given the radius or you're given the diameter, which is basically giving you the radius. You're just going to be plugging in to the right-hand side of these formulas and chugging along. So I call these plug and chug varieties. Real easy. Plug in and get the answer. Let's take a look at one. All right, you and your friends are on spring break, and if you're watching the show right now, you probably are, and if you're watching the show, great spring break. All right, so let's say you're playing with a beach ball. Your mathy friend says, hey, I wonder how much vinyl makes up this ball and how much air is actually inside that ball. And you're like, man, who cares? Let's just have fun. Well, math is fun, so we're going to do this example. Your friend is simply inquiring about the sphere's surface area, which is the amount of material used to construct its outer surface, and the amount of air that this ball contains is its volume. Okay? So this is a good math problem relating to spring break. Now let's assume that it's a big beach ball. Let's assume that the diameter is 3 feet. So that would be straight across from one great circle to the other. It doesn't matter. All great circles pass through the center. Okay? So if that's the diameter, then the radius, remember, is half of the diameter. So if the diameter is 3, we know that the radius is half of 3, or we can use 1.5 feet. Okay? So we did have to do one simple calculation to find the radius, but now that we have the radius, we're ready to rock and roll. Okay? Let's go ahead and find surface area first. I recommend writing out the equation every time, the formula, because it helps you remember it. The formula for the surface area of a sphere is 4 pi r squared. Well, now we'll just plug in. That's 4 times pi, which is a constant, times our radius squared, and our radius is 1.5. About the only mistake you can make up to this point is plugging in a 3 for the diameter instead of finding the radius first. So read very carefully. Drawing pictures and labeling the actual quantities that you're given will help you from doing that. So that's the plug part. Now it's time to chug, and that's where the calculator helps you. Pi is irrational, so I'm going to put an approximation symbol here, but you punch it all in, and you'll get 9 pi, which is about 28.274 square feet. That's the amount of vinyl material that is used to produce this beach ball. Okay? Now onto the question of how much air it holds. That's the capacity. That's the volume. The formula for the volume is 4 divided by 3, or 4/3, times pi r cubed. So we've written down the formula. All we need is the radius, so let's carefully plug in. That's 4/3 times pi times our radius cubed. Notice the way I write this down. For my variable I'm plugging in, I leave little parentheses and cube it, and then that simplifies the process of actually taking my 1.5 and plugging it in. So that's the plug part. The chug part is the calculator. It's about 4.5 pi, which when you punch all that in, gives you about 14.137 cubic feet, or feet cubed. So that would be the air capacity of that beach ball, the maximum amount of volume that it can hold. Okay, so that's a pretty easy problem. Now sometimes you're going to need to find the radius when you're given either the volume or the surface area. So that's not going to be a big deal, because you just want to remember that these equations are literal equations, so we can solve them for either one of the two variables so long as we know what the other one is. They work both ways. Okay, so let's look at an example where we have to do that. All right, still on spring break, we got Jenna. Jenna's on spring break, and she just finished a game of beach ball. She's really thirsty, really dehydrated, so she's going to replenish her electrolytes by peeling and eating a delicious orange. And oranges are much better if you peel them first. Okay? Now when she's done eating her orange, relaxing in the cool spring breeze, she's bored, and she's a math person, so she calculates the amount of orange peel that she peeled off to be roughly 80 square inches. Okay? So the peeling that's left is 80 square inches. She now wants to know what the radius of her orange was because she ate it. So she can actually play mathematical detective here, and just from the remnants of what was already consumed, she can figure out basically the dimensions of the original orange. Pretty cool, huh? It's all with math. Well, the key in this problem is realizing that the peelings is nothing more than the surface area. So if I pull out the surface area equation, it is 4 pi r squared. Now there's two ways you could do this problem. This is not solved for the variable that we're interested in finding, so you can either divide by 4 pi and take the square root, and you'll get an equation that looks like this. You'll get the radius is equal to the surface area divided by 4 pi, and you take the square root, and you only take the positive here because we're interested in a positive radius. This is called the working equation. We modified it with the variables inside of it, but now it's set up ready to go to solve for r. Depending on what your teacher expects, you may or may not have to do that. The other option, which I'll show you here, is just to plug in carefully the given quantities. We know the surface area, so I'll plug in surface area is 80 equals 4 is 4. Pi, remember, is 3.14 times the radius squared. I don't know the radius. Now I can do the algebra and solve for r squared. I'm still going to have to divide both sides by 4 pi, and so I'll get r squared equals 80 over 4 pi, and now taking the square root, the positive square root, we don't want a negative radius, I get this expression, which now the calculator will tell me is about 2.523 inches. Okay? So that was the radius of the orange, so about 2.5. The orange was about a 5-inch diameter orange. That's a pretty good size orange. That ought to do the trick in terms of replenishing the electrolytes. All right, here's a chance for you to go replace your electrolytes, but don't go too far, because I'm going to be right here waiting for you to come back. I'm going to still be around. Well, let's bounce right back into our lesson on spheres. All right, now the problems can get more interesting when you're given neither the radius, nor the diameter, nor the surface area, and you're not even given the volume. Instead, you're given some other quantity. Now, don't panic. In this case, you're just going to have to extract the needed information from what's given. It's kind of like squeezing your own orange juice when you're handed an orange, okay? You're just going to have to do a little bit more work. Not a problem. Don't panic. Find the volume of a sphere whose great circle, or a great circle, has a circumference of 31.4. Now, it may not tell you that the great circle has a circumference of 4. If it just says a sphere has a circumference of 31.4, you can assume that it is also one of the great circles. We use them interchangeably. Okay, so notice, though, that we are given the circumference of a circle, and we're trying to find the volume of the sphere. So I'd like to start with what we're trying to find. We need to find V. The formula is 4/3 pi r cubed. What do I need to know in order to find V? I need to know r, because everything else is a constant. Well, I'm not given r, I'm not given the diameter. All I'm given is the circumference of a circle. Well, if you know it, or you look on the formula chart, there is a formula. So the circumference of a circle C is 2 times pi times r. So here we go off to the side. This is our orange juice little factory. We're going to plug in C, the circumference, 31.4 equals 2 times pi times r. Now I have one equation with one unknown, and I can solve for that unknown. So I just divide both sides by 2 pi, and voila, I have my orange juice, my equivalent to my orange juice. I have my radius. It's 31.4 divided by 2 pi. Now, what do I do with that? Well, I need to plug that number back in over here for r in my volume equation. So, do you want to plug this entire expression in? Well, you could punch it into your calculator, and you're going to see in this case that it comes out pretty close to 5. It's 4.997, which I think we're not going to lose any information if we just call that 5 inches. So let's go ahead and plug 5 in over here. We have the volume is now 4/3 times pi times radius cubed. And again, notice I left a little parentheses. I will now plug in my 5 that I found, and now we're ready to just chug along. So the calculator, again, will help you with this. You can simplify first if you want, but you can plug it in just like this on your calculator, and you get 523.599 inches cubed. So there's the volume. So what did we have to do? We needed to find r. We weren't given r. We were given the circumference. Come off to the side, do a little bit of work to find r, get our solution, plug it into the formula we were interested in, and then we have our answer. Nothing to it. All right, now here's another one that requires a little bit more work, but you got to have this mindset. More work means it's going to be more satisfying when we get to the end result, right? Anything that comes easy is not going to really be as satisfying. In the end, we're going to feel better about something we work hard to get, right? Good attitude. All right. We want to find the volume of a sphere that has a surface area of 615.8. All right? Well, you can probably already determine that the connection between the two formulas for volume and surface area, as I mentioned before, was the radius. And so I'm going to be able to extract the radius from the surface area and use it in my volume equation. So again, I like to start with what it is we're trying to find. We're trying to find volume, so that's V equals 4/3 pi r cubed. Identify what it is we're trying to find. We're trying to find V, so it's okay not to know it, and that means we need to know r. I need r. So where do we go to get r? The other piece of information will give it to us. It's the surface area. So remember, the surface area equation was 4 pi r squared. And I know the surface area, so I can plug in 615.8 equals 4 times pi times r squared. And there it is. It's one equation with one unknown, so we just divide both sides by 4 pi and take the positive square root. And we get this expression, 615.8 divided by 4 pi. And be careful when you plug this into your calculator. I see a lot of people hit the square root, 615.8, divided by, and they just punch 4 pi. You have to either divide by 4 and then divide by pi, or divide by the quantity, put parentheses there. It's a common error that I see all the time. But anyway, if you do that, you're going to get the radius to be approximately 7.0002 inches. Well, I think that 7 inches sounds really good. So again, a nice round answer that's approximate. We're going to plug it in over here now. We've got the information we need. We come back to our other equation, and we get the volume then is 4/3 times pi times our radius cubed. And again, I left a little space for it. Here's the 7. Come on over, 7. Go right in there, please. All right, he fit nicely. Now it's just a chug. Chug. Plug it into your calculator. Here we go. Get the wheels a turning. 4 divided by 3 times pi times 7 caret 3. Enter. Those are the keystrokes on the calculator. You get 1436.755. And always remember your units. It's volume. We're dealing with inches. So this would be cubic inches. And there you go. Okay? So don't panic. Just take what's given, identify what you're trying to find and what you need to get there, and then play a little mathematical detective, okay? It's kind of fun if you just change your mindset. Now, sometimes the calculations require a little ingenuity and a combination of formulas. Here's an example. A pharmacist, okay? Good profession. They help people with medication, and medication can sometimes come in the form of a capsule, okay? And a capsule is going to be, I have 2 of them here. These are tablets, these are capsules. So a pharmacist is filling medicine into these capsules, and the capsules are nothing more than cylinders with half spheres on each end. So if you want to look at one kind of laying flat, it looks kind of like this. We have basically a hemisphere and a hemisphere, and then we have the cross-section is a rectangle. So in the 3-dimensional, this is really our cylinder, another cylinder, and then we have 2 halves of a sphere. Okay, so that's what it's composed of. If the length of the capsule is 16, so that's going to be from here to here all the way across. That capsule is 16 millimeters long. And we know that the radius is 2 millimeters long. Well, the radius is going to be from here, which is the halfway point. It's going to be basically half of this. It's 2 millimeters. So it's right here. If you want to draw it on this side, it's going to be this distance right here, because our radius on that hemisphere will stem out all around. So what can we do now? We need to know the volume of the capsule, because we're trying to figure out how many cubic millimeters of medication can one capsule hold. Hold is implying capacity, and cubic is another Q. Cubic is volume. So you need to read carefully. Are we trying to find the surface area or the volume? So there's some verbal cues in there. So let's start with a template. I know the volume of the capsule is going to be a combination of the volume of the cylinder plus 2 times, I have 1 on each side, but these are half spheres. So 2 times 1/2 the volume of a sphere. Okay, so that's starting off with a real big template. Now I can kind of get specific. The volume of a cylinder, if you remember from a previous episode or from a formula chart, is pi r squared h plus 2 times 1/2. Well, this right here, that just goes to 1. In other words, if I take this hemisphere and this hemisphere and I combine them together, I just have the volume of one sphere. Well, that's upon today's show. We know that to be 4/3 pi r cubed. So now I have some specifics here I can plug into. So let's talk about the cylinder. The cylinder is going to require me to know r and h, the height of the cylinder. Well, r, if we come over here, r is going to be the radius of the face, which is the same as the radius of my hemisphere, which is 2. So that's 2 squared times the height. Now here's where we need to be careful. We're talking about the height of the cylinder. We know that the total length of the capsule is 16, but that's from here to here. And remember that from here to here is 2, and also from here to here is 2. So what I want is I want what's left over. That's the height of the cylinder between the hemispheres. So it's going to be 16 minus this 2 minus that 2, or 16 minus 4, and that gives us 12. So drawing a picture is very, very important in getting the right answer. All right? So there's the volume of the cylinder. Now I can go ahead and plug in over here. That's plus 4/3 pi times the radius of the sphere, which is still 2 cubed. Okay, so now I've got it all plugged in very carefully. I didn't just get excited and plug in the 16 that was given. I deliberately looked to see what I needed, and I found the height of the cylinder was 12. So now it's a chug variety. You plug all that in, and you will get the answer, which is approximately 184.307 cubic millimeters. Okay? So that is the volume, that is the capacity of one of those capsules. It can hold no more than this amount of medicine. Okay? Now it's time for the Say What? And if you liked last week's Say What about Archimedes, and you were kind of curious to what I alluded about a mathematician streaking, I'm going to talk about Archimedes again today. So Archimedes Part 2. Archimedes has this famous moment called the Eureka moment. And Eureka is become a phrase that is synonymous with discovery. Discover gold, Eureka. Well, Archimedes said Eureka when he discovered something. And here's basically what the story says. It says that the king, or the tyrant Hero was his name. He was the king of Syracuse in the time of Archimedes. He proposed this puzzle to Archimedes. See, he wanted to have this crown built for him. So he hired this artisan, and he gave him a lump sum of gold. Well, he didn't really trust the artisan, and he was suspicious that the artisan might try to use some cheaper alloy that was combined with silver, which was less expensive and it was less dense, and that would allow the artisan then to produce a crown that looked like it was made of pure gold, but it wasn't, and then the artisan was able to quietly pocket the difference and make a little money on the side, thinking that the king would be none the wiser. Well, the king knew about Archimedes and gave the task to Archimedes to try and discover if in fact the crown was made of the pure gold he had given the artisan, or if he had mixed it or substituted with it some cheaper alloy. Okay? Now, how in the heck is Archimedes back in 300 BC going to figure this out? Well, according to the traditional tale, it came to him, the answer came to him while he was stepping into the bath. Okay? He noticed that as he stepped into the bath, and as he immersed himself, lowered him into it, the water level rose up. He was displacing water, and that his weight seemed to decrease. He became lighter. Okay? Now it came to him in a flash. He was so excited, he dropped what he was reading, he jumped out of the tub, and he was said to have run through the streets of Syracuse, totally naked, screaming, "Eureka, Eureka," which means, "I have found it, I have found it." So what did he discover? Well, what he was talking about was known today as the principle of fluid buoyancy. He realized that two objects of equal weight will displace different volumes of water if they have different densities. And today that principle is actually known as Archimedes' principle. So if the silver alloy was in the crown, it would displace less water than the crown that contained pure gold, because gold is denser than silver. And so by taking an equal amount of gold that the crown was supposedly supposed to be made out of, and the crown itself, he can compare just how much the water level rose. Fluid displacement as opposed to actually calculating volume. Very ingenious. Whew. Well, I hate to burst your bubble, but we're out of time for today. It goes so quickly. Hope you learned something today. And remember, if there's something that you're unsure about, you can always email me. So log on to the district website. My email address is right there. Send me an email. I'll be happy to answer your questions. So until next time, I'm Kevin Corpy, reminding you to have a very fun, safe, mathematical, pleasing spring break. And I'll catch you on the flip side.